So, good morning, ladies and gentlemen. I think for half an hour you should imagine that you have Yoichiro Nambu in front of you. That may not be easy, but anyway, I'm very honored to replace him today, but it's a great responsibility because actually you will read in the book the lecture that he's going to write, but he sent me only some preliminary notes, and said, do it your own way. But I've known Nambu since a very long time, since I was a co-author of his first papers on this topic. And so I will try to stick as much as possible to his way of thinking that actually I think I know quite well. And so the title, Spontaneous Symmetry Breaking in Particle Physics, a case of cross-fertilization. Cross-fertilization is when some ideas flow from one sector of science to another one. And this was a very important case. I will try to tell you how all this happened and which were the various steps in the introduction of this new idea into particle physics. So, there is a proverb in every language, I believe, that history repeats itself. And it's particularly suitable for this case. Why? You see, this is the first time that this idea of spontaneous breakdown was presented in a public conference. There had been a mention in a talk by Nambu in Kiev in '59, but the first systematic presentation was at the Midwest Conference in Theoretical Physics in 1960. I was working with him, and also in that case, he couldn't come. He had been invited. He told me just, I think one day before, well, you go and you do it your own way. So I must say that the night before the presentation, I didn't sleep much. And I was very worried because, as I will tell you, this is based on an analogy with the theory of superconductivity, which was had been proposed 3 years before by Bardeen, Cooper, and Schrieffer. And I knew that Bardeen and Schrieffer would be there. So anyway, everything went well. And so now the circle is closed because I replaced Nambu on this very important occasion. Now, I think also this text is very important because this first paragraph tells you what is the spirit of this idea. And at that time, people recognized that there are many similarities in language when you do what was called many-body theory, so condensed matter theory, and elementary particles, where the natural language is quantum field theory. And so, for example, he emphasizes the analogy between the Fermi sea of electrons in a metal and the Dirac sea of electrons in the vacuum. But then he also says, of course, in elementary particle physics we have more symmetries and invariance properties than in the other, and blind analogies are often dangerous. So we now, to understand how this cross-fertilization took place, I will quote from the preliminary notes that he sent me, and where he tells about his story in Japan, where he he was exposed for a certain time to condensed matter physics, and which was at that time, I mean, as he emphasizes, pretty good in Tokyo. And then he went into particle physics after the war, and he says that my early exposure to condensed matter physics has been quite beneficial to me. In fact, I mean, this idea of spontaneous breakdown is an idea which was common in condensed matter, even though there was not much theory about it. It was not so much recognized as a symmetry breaking. It was, and now I will describe you a few examples very briefly. So this is an example of spontaneous breakdown that I like because it's part of everyday's experience. I think everybody has done such an experience. If you take a bar, an elastic bar, and you compress it, first, if the force is weak, that you get a contraction according to Hooke's law. But then at some point, when the force becomes sufficiently strong, then the bar gets inflected. And so this is a typical case of spontaneous symmetry breaking, because at some point the equilibrium state becomes the inflected state. And you see that why have you lost the symmetry? Because now this bar lies in a plane, but the orientation of this plane is completely arbitrary. And so you have a phenomenon which is new, which is that the equilibrium state is a degenerate state. And it's important also to realize that the reason why you get this new state is the fact that the internal dynamics of the bar is essential. I mean, classically it's described by the theory of elasticity. Now, let's mention other examples. Another very common example is the fact that metals get magnetization, so all the spin, as it has been mentioned before, get oriented in the same way, while the laws of nature are entirely symmetrical about rotation, and now we have, again, a degeneracy of the state because the orientation can be anything. Then crystals. This is also a very important case of spontaneous symmetry breaking because in this case, you break a translational invariance, and because you get a regular structure. So, I mean, there is a minimal step that you have to make in order to have a similar state. Then we have superconductors and superfluid helium. In this case, the symmetry which is broken is more abstract, so it's less intuitive, but we shall have to elaborate on this because of the topic I'm going to discuss. Anyway, so far you have to retain the fact that there are cases in condensed matter where a symmetry is broken, and then the ground state is actually degenerate. So there is not a preferred one in... Now, how did it start, this in interest of Nambu for superconductivity? So he mentioned that before the publication of the Bardeen, Cooper, and Schrieffer paper, Schrieffer, who was still a student, came to Chicago to give a seminar, and he was disturbed by the fact that the wave function did not conserve the electron number. So the wave function, in fact, did not respect gauge invariance, which is the symmetry which is broken in this case. But he was, at the same time as I was impressed by their boldness and trying to understand the problem. So, and he worked for a couple of years on superconductivity, and he produced a very beautiful paper, which was published in 1960, where he finally I couldn't understand in detail why also in the theory of Bardeen-Cooper-Schrieffer actually gauge invariance, which more concretely means the conservation of charge is not destroyed. So what is the mechanism of the Bardeen-Cooper and Schrieffer theory? The mechanism is that you have in a metal the Fermi surface. At low temperature, this is filled with electrons. But the interaction between electrons is mediated by phonons. And it turns out to be near the Fermi surface to be attractive. So there are pairs which are formed. And these pairs just are similar to bound states. Actually, it's a collective effect. And the wave functions of these pairs is rather spread in space. So they overlap, all these pairs, with each other. But in order to get conduction, you have to break this pair state, and this takes a finite energy. That's why the mechanism of superconductivity sets in. So, and this is how I take again from a recent short paper by Nambu the explanation. Now, let's see a little bit more in detail what happens in a superconductor. You have, in order to break these pair states of electrons of opposite momentum and opposite spin, and then you get some kind of excitations which have a rather peculiar structure. You see, when an electron is taken out of the Fermi sea, you get there is a hole which is produced in the system, and this excitation, so it does not have a definite charge, but it's a superposition of different charges, and these are the equations that appear in the Bardeen-Cooper and Schrieffer theory, and the eigenvalues, as you see, contain this phi parameter, which is called the gap. And in fact, that is the twice this value of phi is the energy that you have to spend to raise the electron into a conduction band. Now, I arrived in Chicago in fall of '59, and I remember that the first thing that Nambu explained to me, I was a young research associate, was the analogy between this equation and the Dirac equation. So keep in mind these two simple linear equations and the form of the eigenvalue, and then we go to the Dirac equation. So the Dirac equation has the same structure. Of course, I mean, you have four components because we are in a relativistic case, but then again, you see the the similarity between, so you see that the mass of a fermion, of a Dirac particle, appears exactly in the same way as the gap in a superconductor. And these states, which were the electron states in the previous slide, now are states which are eigenstates of an operator which is called chirality, which is connected with the spin of the Fermi particles. Now, Nambu studied in detail the structure of this problem, of the BCS theory, and then he understood how the conservation of charge is restored in the superconductor. So you have that these excitations, which are called quasi-particles, are described by a certain field rho. But then, in order to restore the charge conservation, these quasi-particles are surrounded by another field of which is in fact produced by these pairs that I mentioned before. They're usually called Cooper's pairs. And so the total charge and current contains two terms. One is connected with the excitation, and the other one is this surrounding field. And the conservation of charge is restored by an exchange of charge between the excitation and this surrounding field. And so you see that, and this is this equation you can find in this paper of Nambu and describe quite intuitively what happens in this case. However, and this will become very important for later discussion, actually these long-range excitations, which then took the name of Nambu-Goldstone bosons, actually do not stay there. Why? Because there is the Coulomb interaction, which is also long range, and the two things interact with each other. And what happens is that when you take into consideration the Coulomb force, the spectrum of these surrounding excitations is shifted to what is known as the plasma frequency. And so essentially this surrounding field of long-range field acquires a mass. So it becomes short-ranged. So this was the situation when, and as I mentioned before, there was this analogy with the Dirac equation. Now this is how the analogy was formulated to get into particle physics. So in the superconductor, you have the electromagnetic currents. In the elementary particle case, there is an object called axial currents, which is fundamental in the theory of weak interactions, and had been the theory of weak interaction had been formulated some years before by Feynman and Gell-Mann. And now he made a correspondence between the electromagnetic current and the axial current. So, and then this analogy could be followed in quite a detail. Now, suppose first that it was not known that whether the axial current was exactly conserved. Actually, the indications were that it was not exactly conserved. And in case of exact conservation, you get the following structure for the X matrix elements. And here we find again the same phenomena that Nambu had found in superconductivity. You get the appearance of this singularity at Q equal to 0, and this is the sign that there exist particles of zero mass. And this was, so you see, if you have this axial current conservation, the mass of the fermion should be exactly 0, but actually the discovery was that it can be different from 0, provided there exist these zero mass particles that are expressed in the form of this expression. So that's, however, so far would be only an indication. And at this point, Nambu made a rather bold assumption that actually current is not exactly conserved, and this causes the mass of this zero mass particle to be different from 0. And so in this case, if in this case, the form of the expression we had before is slightly different. Now you have the singularity q equals 0 has disappeared, and this expression implies an important relationship between various coupling constant and the mass of the nucleon. That was the particle which he had in mind at that time. So this is the constant of weak interaction. This is the strong force. So it's the interaction between pion and nucleon. Okay, and then the decay constant of the pion. And this was known at the time as the Goldberger and Freeman relation. When I arrived in Chicago, Nambu asked me to check all this calculation. This was our first interaction. And but at that point, you know, as he had said in the first slide I've shown, one has to be careful with blind analogies. And you know, it could be purely formal. And so we have to see whether one could actually introduce it in a more reasonable relativistic theory, in a model of interacting particles. So at that time we made a preliminary calculation, which we didn't take too seriously because I mean, it was perturbation theory with strong interactions, but we got an encouraging result because, in fact, we discovered that even in this rough calculation, if you have a mass of the pion, which was the zero mass boson originally, and the renormalization and the coupling constant of the weak interaction, they went in the same direction. So apparently, the same cause could be the cause of the mass of the pion and the renormalization and the intensity of the weak force. And this also was important in my relationship with Nambu because I did this calculation. At first, he was not convinced, but then he accepted it, and he told me, "You won." And then our relation became a full-time collaboration, and which went on for the whole year. Then we produced a model which was exactly axial invariant. And this reminds of a theory that Heisenberg and collaborators had produced in those years. And in the Heisenberg theory, there was the idea of spontaneous breakdown, but it was mixed with so many other things because they pretended to solve all the dynamics that people did not understand really what was going on. And in fact, there was no physical consequence of that theory. So what was interesting was the spectrum that we found in this model. Of course, since the model is not renormalizable according to the usual quantum field theory, we had to introduce a cutoff. So it was some kind of effective theory, and but there was a very rich spectrum. There was, of course, the fermion spectrum, so the Fermi particle was allowed to have a mass. Then we had a spectrum of bosons. There was the zero mass boson. There was, and that is interesting, a scalar particle which had twice the mass of the fermion. This actually is, it's interesting because at times it has been identified with the Higgs particle. And this type of excitation has actually been found in superconductor. In 1980, there were measurements which found this excitation. And then there were various kinds of vector mesons. So once you admit that the theory made sense, you got a very rich spectrum. Now, at that time, of course, it was purely a model, but let me mention another example where this type of mechanism seems to be operating. One is the superfluidity of helium-3, which was discovered several years later. And also to this, Nambu gave a contribution. He found the sum rule, which is in a paper of 1985. Then similar phenomena you get in nucleon pairing in nuclei. And then the fermion mass generation in the electroweak sector of the Standard Model. Now, there are various interpretations of the Higgs model, but his, as I say, his biased opinion is that actually this is again a case of okay, so maybe we have to accelerate. And so now the next step was the so-called Engler-Braut-Higgs mechanism, but there had been a paper by Anderson the year before, where they realized, Anderson realized that the mechanism which gave a mass to the zero mass excitation in superconductivity actually could give a mass to the vector mesons. So again, a symmetry could be exact, and then you get the mass of the particles. And well, Nambu said that he regretted not having done that himself. And I must say that I also have to join him in this regret, because I had the same elements that he had. And now, when this spontaneous breakdown mechanism became real physical theory, it happened with the Weinberg model of weak interaction. And if you read the last sentence, we might hope to understand this difference in masses of the vector mesons, relating the weak and electromagnetic. They imagine that the symmetries relating weak and electromagnetic interaction are exact symmetries, but they are broken by the vacuum. So it's again the mechanism of spontaneous breakdown. Then our model became an effective theory. There's been an enormous literature. Well, I think I will not spend time on this, but it gave rise to a very extended phenomenological theory, which is called also chiral perturbation theory. And now let me come to the present-day views of Nambu. There is a big problem in elementary particle physics, which is the hierarchy of masses. Masses cover a large spectrum of scales, and but they're not so regular. I mean, masses are an effect of the dynamics, so it's and we are usually not able to solve exactly the dynamics. And the masses form hierarchies, like everything else in the universe. Now, Nambu likes to quote this an opinion of Einstein that says, and the opinion is that in the fundamental equation of gravity, you have a beautiful part, which is the left-hand side, which has a geometrical interpretation, and the right-hand side, which has, it's ugly. I mean, there are the different matter fields which contribute to as sources of gravity. So the question is, can one geometrize the matter field and shift everything to the left? And that is this idea of hierarchical spontaneous breakdown of symmetry. So you see, the idea is to have a cascade of spontaneous breakdowns. For example, the typical example is what is indicated here. You have, I mentioned crystals as a case of spontaneous breakdown, and then the Nambu-Goldstone bosons associated to crystals are the phonons. Then the phonons provide the interaction of the electrons, and then you get again a spontaneous symmetry breaking for superconductivity, and so on. You can do a parallel consideration in the case of elementary particles. So you have the quantum chronodynamics, which is chiral invariant. With time, nucleons were replaced by quarks, and then you have hadrons, pi and sigma mesons, then nuclei, nucleon pairing, and then you have the analog modes in the nuclear collective modes. So this is a very interesting point of view, and I think it has to be taken seriously, and Nambu has had many important intuitions in his life. So that's essentially the end of my talk. It had to be very rapid overview. And let me just add, in recollection of my old collaboration with Nambu, let me just show you a picture. So this was taken in relatively recent times, and one sees that many years have elapsed since the time, but which was for me one of the richest period in my scientific life. Thank you.
Thank you very much, Professor Jonas Lasinio, for this very interesting talk, and on behalf of Professor Nambu, thank you.